Question letter B is going to ask us to find G prime and G double prime, which is going to involve a little bit of strategic thinking. The logic here is that if they give us something like -3 to plug into an existing function, then we just have to follow the rules. Plug into G prime and call it a day. But since they didn't give us G prime, we're going to have to use a bit of logic. And that's where I want to make sure that I do a bit of side work first to ensure that the logic for where G prime comes from actually makes sense. G prime would naturally be the derivative of G. So notation-wise, I'm going to take a slightly different approach. You'll understand why, of course, if you've been watching some of these other videos. I want to find the derivative of G. That's what G prime means, derivative of G. And that involves taking the derivative of the G function, the integral from 1 to x of f of t dt. If you've seen these before, you probably already kind of know where this is going. The derivative of G is G prime, so it's not like anything's really happened with my notation on the left, but recognizing this notation on the right probably triggered some of our memories of the second fundamental theorem of calculus, which is where we say, hey, the derivative and the integral, those cancel each other out. So to utilize the second fundamental theorem, we'll basically say, hey, the derivative of the integral is going to cancel. That leaves us with whatever the original f function was, and we'll plug in the x to where the dummy variable was. Now we're technically also supposed to multiply by the derivative of whatever we plugged in, so the derivative of x is just 1, but that of course is trivial because multiplying by 1 isn't going to change anything. So G prime, the function that they want us to be able to use, is really just f of x. And that relationship, which you may recall seeing in previous examples, is so important that I'm going to highlight it. I'm going to color code it even, because that's something that we need to know. If this question wants us to find G prime of -3, they're really asking us to find f of -3. And we don't have to actually do anything with G prime specifically. We can train our attention instead to the f graph because we know something about the graph. One thing that we found about these questions, which makes things so easy, is that if you just have to find f of something, that's just finding function values. Some people call them y-coordinates on the graph. And if that helps, then you can certainly think of this question not as G prime of -3, but what's the y-coordinate on the graph at the x-coordinate -3. That seems to be a way easier interpretation, and that's something we can do. If we look at the graph, -3 would be 1, 2, 3 here. -3 isn't really a labeled point, but we can use a bit of logic, because if this point here at -4 is at 1, and this point all the way up at the top of the line is 3, halfway between them would be -3, 2, so the y-coordinate at that point must be 2. Linear functions make that assumption much easier. And then, of course, I'm done. Now, of course, you don't actually ever have to show this derivation that I showed on scratch work. I would move my scratch work to the side and only show this if I was asked such a question on the AP test. But it is worth noting that if you're still not sure how to get G prime information, this is what you would do. Take the derivative of G, take the derivative of the function you're given, and utilize the second fundamental theorem. If you want to skip that step because you already know that the derivative of G just means y-coordinates of f, then of course take that shortcut. But once we have established that that fundamental theorem is important, that should also theoretically help us with G double prime, because G double prime is the same logical idea. G double prime of -3 involves taking a derivative of G prime. So I'm just going to think logically, again with my side work here. G double prime would be the derivative of G prime, which means the derivative of G prime is the derivative of f. The derivative of f would be f prime, which on its own doesn't seem like it's all that important, but in the context of a graph can be extremely helpful. F prime is just slopes on a graph. So if I can look at the graph and tell what the slope is at a specific point, then I can eschew this need to do G double prime, and I'll instead just worry about f prime. I'll just worry about slopes. So So g double prime of negative 3 is really f prime of negative 3. And that's really just saying, hey, find some slopes. Or one specific slope, actually. One specific slope at negative 3. So at negative 3, again, I'm at this line. So I can find its slope by counting rise over run. I would need to go up 2 over 2 to get the slope. So up 2 over 2 would be a slope of 1. Thus, my slope is 1. Therefore, g double prime is 1. That's the beauty of the second fundamental theorem, knowing that these relationships can be found on the graph by simply converting those relationships from terms of g to terms of f. By putting it in the terms that the graph was dictated to use, then all of a sudden we could use the graph for its intended purpose. In letter C, we're going to, again, continue to use these relationships. If you feel like you can do letter C, I'll give you a hint. You'll need to think about which of these relationships really kind of goes with some of these key words. You have keywords like horizontal tangent line. You have keywords like minimum, maximum. And for all of those things, we know that one of these relationships is intrinsically linked. Think for yourself about which relationship that is, and if possible, try letter C on your own. If not, in the next video, I'll walk you through.